Hello, this is Aaron Bose from Cray, and I'm here today to talk about MPI on the Cray XC30. I'll be doing a little bit of comparison with Cray XC6 or XK7 system, similar to the Titan supercomputer. We'll try to focus primarily on the XC30. I'll give you an overview. We're going to talk about the Cray library, some of the optimization techniques that are done. And the primary focus will be different pathways that MPI messages can take through the system. There's 4 primary pathways that we're going to talk about. And then this is going to bring up some environment variables that we can control with these images take, and then some other operations. And finally, I'll talk a little bit about the progress engine that can hopefully allow you to overlap communication with application as the MPI progress engine can make some progress with the state while your application is computing. So we'll touch on that a little bit towards the end. So, Cray guide library started out pretty much the standard MPI from Argonne National Labs. It's a good start. Feature, it's robust, it's stable, it's tried and tested, it's a great starting point. Cray adds a whole bunch of two versions. Primarily, that's low-level communication library and then performance tuning for point-to-point and collective operations across nodes. So that would be, say, inter-node, not intra-node communication. That's where a lot of the performance tuning is done. And in addition, there is some tuning of intra-node communication with PMEM, which I'll try to bring you right. So, just thing I should mention here is that on the left you should see what would be typical of, say, the Titan supercomputer. It's an XC6 or XK7, and the XC30 is on the right. And the first thing you'll probably notice is that there aren't very many differences between these two pictures. Right. Look at this, you probably see the only difference is that on the left there's the word Gemini that refers to network. Interconnected Gemini interconnect. And on the right, you see Aries, where you saw Gemini. So the two software stacks are very, very similar, and especially from a user perspective, really not a whole lot as far as the software stack that you need to be concerned with. This is backwards compatible. A lot of your experience and intuition with the previous software is still through today. There's a continuity here in the software stack. That point, detail is super important. The one thing I would point out, though, is that there are optimizations you can see that allow the bypassing of operating system as the user-level GNI, which is the generic network interface, and DMAP, which is the distributed memory API, are able to directly access the hardware abstraction layer and bypass the kernel. So that does a lot to improve provide for low latency. So as I mentioned, there are main pathways split into 2 main categories you'll see here. There's the ear message path for generally for small and rendezvous message path. The one path you see for large messages. And since this slide does bring up the intra-node messages optimizations, I'll talk a little bit about XPMEM. So generally, if you have one process or one thread on that wanted to communicate with another processor thread on the same node, the Cray historically would take your MPI transfers between these 2 processes, and it would essentially optimize a way all of the MPI stuff, and what would happen if the core would be a mem copy. So the standard routine. And XPMem is a new kernel enhancement, relatively new, that would have taken the place of this mem copy. And the idea is that mem copy usually happens from one of the ranks into a system or a library memory buffer, and then it's copied from that system or library memory buffer into the rank for the other process. So there are two copies happening here. And XM attempts to bypass that by taking advantage of, well, essentially the management system that's in the hardware on common x86 system, right there. So the idea that you take the buffer on the sending process, you don't necessarily have to patch it from the sending process, but just for somebody I'll talk about like that. You'll detach that memory from the sending process by removing entries from the sending process's table so that those don't refer to this anymore. And then this buffer is attached to the destination process by, again, changing the page tables describing the memory layout of the process. This buffer is going to belong to the receiving process. So what's happened here is just the structures in the page table have been modified so that the data belongs to a different process, is the way it looks like. And the receiving process, since it owns this buffer, can do a single mem copy from this newly buffer entry that was already part of the receiving process. And then you can just buffer from the receiving process reattached to the sender. And I know I talked detaching when really the memory could be attached to multiple processes, but it's a little easier to think about. So this is all only attached to a single process. But XPMem, it can advantage of the page table to avoid an unnecessary extra. Right. So a little bit first, I mentioned slow transfers and fast transfers. Generally, the fast transfers use this SMA, stands for memory access. It's called code, so it bypasses most of the kernel. It's good low latency. And then the other option for large transfers is called a block engine. This is managed from kernel base. So once transferred, an MPI rank can continue to do processing, and then in the background, the kernel can take to this block transfer and use it. So I point out that all of the nodes share resources. So there are 4 virtual channels per node. See 4 transfers. I mentioned these 4 pathways based on the message style. So this bottom of slide 7 should give you some kind of idea of, I don't know necessarily the exact default that are used in every system, but it should give you at least some idea of how large the message is, what path would it take. So you have 112 bytes. We'll take the path, the E1 path up to 8 bytes. And then what you hear in green, with the arrows pointing to the divisions between 4 columns, is environment variable that you can use to change the transition. So, for example, you see in-pitch GNI max V short message size set to 512. That find the boundary between taking the E0 and E1 path as 512 bytes message. So anything larger would take E1 up to the max E1 path, and smaller would take 0. And so there are the environment variables defining all of the thresholds. So you can environment variables to choose which message will take. There are consequences to that, which we'll talk about a little later. And I want to personally apologize for these names, right? These three things are really the three steps in the paths to take. What one would think maybe names could be a regular, consistent with each other, but that's what we live with. So, and again, we pretty much talked about all of this. The primary to point out, though, are, I suppose, between doing E1. We know that it's on message size, but why? And the idea is that the small message mailboxes attached to the stack, and these mailboxes have a finite size. So if something can fit in a small message mailbox, it's an easy message. If it cannot fit in a small mailbox, but it's enough to fit in larger MPI, generic MPI buffers, you can go to E1. Trying to show visually how this would be done. Sender first will initiate a send. That send will go directly to the receiver's small message mailbox. And if there's a mailbox available, then that receive is done, and an min copy will transfer the actual message data from the small message mailbox to the buffer in that user processes as space. So there's this extra min copy, but it's pretty simple, pretty forward. A bit more complicated in the next pathway, the E1 way. So the sender sends directly to the receiver with header and the data, since it won't fit in the mailbox available. The very first step is to copy the sender's data into a local MPI buffer. Then just the small message send MPI header, which is basically just a header. And the receiver, in step 3, you see in red, can issue an RDMA get operation, get that data from the sender, place it in the local MPI buffer. He can respond to say the receive is done, so the sender knows that the data has been received. And the point, sort of the last step is the receiver can copy out this local buffer receiver's address space, and the sender could free its gated buffer use. So you can see this involves many more steps. 7 network transfers. And the E1 pathway has a higher latency, but still lower than something invoking the fault transfer can do. So you can see that the E1 pathway is used when it cannot fit in those small message mailboxes. So eager pathways, and the pathways, eager methods, larger images are the rendezvous pathways we talk about here. And I'd like to make here is that I guess the thing to do would be to try to use the R1 pathway to maximize the computation and communication overlap with progresses. You can get some overlap with the R0 pathway, but if you're already in the regime where you have large message transfers, you're done, the message transfers are probably going to be relatively slow, so you really want to get as much overlap as possible. Visually look at these things. Zero pathway, you can see similar, I suppose, to the E1 pathway in the sense that the very first operation is not the send of the MPI header data. Right? It cannot in the mailbox, so only the header and no data. But then after, the buffer once the send is registered. So you saw in E1 case that a copy was done to MPI buffer. And the sender is sending so much data that is not space the MPI buffers to buffer this. So what's going to happen is the sender's memory region in vendor can issue an argument get to actually hold data in, and then at this point, it can be sent back to the server so the sender knows that the action is complete, and then to clean up these buffers in the sender and receiver can be de-registered from the network's local MPI links. And this registration operation is actually expensive. There's a couple of variables that we know later. Our one is very similar, but it involves even larger messages. So generally, they're too large to issue in a single RDMA get. So what you'll hear in the note at the bottom is to repeat steps 2 through 6. So again, you'll send a message with the MPI header. In this case, receiver registers first. The server will register its chunk, send to the receiver, and then once send to the receiver is done with the RDMA input, a message can be sent back to the receiver saying that send was done. So then the receiver can unregister the chunk that it just used, register the next chunk, and start over. So your steps 2 through 6 will happen. And for the large buffer, one chunk. The big thing I think to point out here is that the chunk size is controlled by MPI, GNI, max, and dereg size. And this can have a large impact on performance, especially if your transfer size is not an even multiple of the chunk size. Really, to get a clean such that each transfer uses a full chunk can just to tune this variable. So finally, we'll come to the MPI progress, and this is a lot more important, I think, in the XC30 than it was perhaps on the XE or X7 XE system type. Some of these features, some of the latest features are just now coming to the platform that have been available for quite some time now. But the idea here is to offer a thread that can, again, progress the state of the MPI transfers while computation is happening. And I mean that the XC30 does this better because there is hardware resources available on the network to help out with this, where there isn't as much hardware support on the XC6, XC7 system, and so it involves a little bit more CPU offloaded on the XC30 system. Here I give some examples of how to turn this on. Just need sure to, flag and enable max thread safety. I don't know the exact details of why that's needed, but it is needed, probably because there's extra help with touch some in MPI, in terms of MPI needs to be sure that those are like. Talk about some of the environments that can tune these the three splits on message size we talked about earlier are probably the most important. But there are some other ones. We understand that there's a limited number of these small message mailboxes that receive eager messages. We can tune the number of those buffers. So if you know that your application actually does send a lot of those small messages, take the eager pathway, and it could improve performance to be sure that you have enough of these eager message buffers available. Otherwise, there's going to be some blocking, right? So one process is waiting for, another to be. So you can see 8 and 9 number. And there's some consequences, primarily this is going to increase the amount of memory that's used on the receivers. That's the case, especially for collective operations. So if you all do one transfer, that was one rank. It's going to be a whole bunch of transfers all at once. And if you want a mailbox for all of those transfers, you might find that you run out of memory available and you can't run all. So you want to be too aggressive with trying to be and earlier on that Cray heavily optimizes the point in the collective operations, and some codes this hurts performance. For codes it makes things better, right? I mean, you wouldn't do it if it didn't make things better for most people. So, but if you find that your application is a little bit like the typical application, you can turn off these optimizations. In this example, in the second point, you see I'm turning on MPI all gather optimization. So you wanted to turn all to all reloaded. There's a bunch of different calls stable individual if you that might be happening. And additionally, the mailbox resources associated with that small message mailbox I talked about are generally allocated on demand by default, and so that can hurt performance. It may be the case that you want to go ahead and pay a heavy startup cost to do all of this allocation. So if you want to give that, you can disable the MPI GNI dynamic form flag, and this will cause all of those mailbox information to be allocated after start instead of when you So for a couple more here, there is a couple bolts that are used for the small mailboxes that aren't quite default. They are default, I guess that's what I would say. So is usually small message mailboxes. This may have to fit somewhere. And if you're familiar with the hardware, the XK6, XE6, or the XC30, these are Newman nodes. So in some sense, the memory width and the latency available between pieces of memory is uniform. And some of this memory is going to be closer to the network card, and some of this memory is going to be farther away. And by default, those message memory are allocated on the memory attached to the process. The first call is default to response, and then that's the allocation. And imagine this is going to put, maybe a typical example, half of your memory on the memory that's close to the network card, and half on the memory that's a little bit further away. And this can hurt performance. So there's this MPI CH GNI inbox placement, when you set to NIC, will cause the first 4096 mailboxes to be trained to be placed on die. So this should a lot of these small messages a lot closer to the actual Aries network card, and so significant performance. In testing, it was found that this doesn't improve performance consistently enough to make it a default, but it's that I think is always worth the time. And then here, I should point out, I don't need mixed codes, mixed technology codes are really there. I suppose there's a few, but if you have a code that's using a lot of these technologies, if you're using MPI and SHMIM, you're using MPI and have a CAF code, sometimes this has some problems. So you can set this flag if you see errors, and many times this is it's a quick fix if this happens to be the problem that you're seeing. It may reduce performance slightly, but if they run, that's better than if they don't. And then highlight him. Main here, not two rendezvous and environment variables, hold mesh sizes, how is it given sizes take. So you'd be again the boundary between the E0 and one pathway, or zero pathway, or one pathway. And these are probably three of the easiest change environment variables that may have a reason for impact on performance. So I would definitely recommend. And the other, especially on the XC30, that I would recommend giving a try in particular is to track the MPI progress. At some point in the future, this is probably going to become default, but at the moment it isn't quite there yet. So go ahead, turn on these three flags, rebuild your application. And I believe what I've been hearing from people like Cray is that you might see performance increase of about 10% on average. So some applications are going through better. I talked to someone at O&O who tried this, and they actually hurt performance application by about 10%. So again, these are not where, but there is in some sense an optimal setting if all offset properly. You can get a bit more performance in this case, a lot of performance. So I believe that's all slides I have.